Following up from his introduction yesterday, Professor Andrew Stuchbery. Welcome back.
Thank you very much. Well, it's nice to be back here and to have the opportunity to give another lecture on nuclear power. So I've entitled this one Nuclear Power Technology, and what I want to talk about is some more physics of reactor technology, a little bit more specifics about how reactors actually work. We'll do a little bit of an overview of alternative reactor technologies. Most of the emphasis so far has been on light water reactors. I'd like to say a little bit about accidents and safety strategies, and a little bit about waste management, and then at the end we can go back to the pros and cons. So let me just review a couple of points from yesterday. We're talking about nuclear fission energy. We're talking about nuclei splitting apart and getting energy out that essentially comes from the Coulomb repulsion of the two fission fragments. Now, in that process, we produce neutrons. Remember, there's 2 or 3 neutrons per fission that come out of the fission fragments, and they have an energy distribution that looks something like this. It's like the energy distribution of molecules in a gas. It's called a Maxwellian distribution, but this is a much higher energy and a much higher equivalent temperature than the temperature in a typical gas. I think if you do the numbers, it comes out to the equivalent of something like 10 to the power of 10 Kelvin. Okay, now, we also introduced the concept of a chain reaction. So we start off with 1 neutron, fissions 1 nucleus, we get 2 neutrons, which in principle could fission 2 nuclei. And if it keeps on growing exponentially like this, we have an uncontrolled reaction, which is not what we want. Let me introduce this concept of neutron generations. We would call this the first generation of neutrons, this the second generation, and this the third generation. Now, what we want to do now is think about neutron generations and reactors and sustaining criticality. So the quantity that is used that's important is this factor called K, the neutron multiplication factor, which is just the number of neutrons in one generation divided by the number of neutrons in the previous generation. So if we have a controlled reaction, you want K to be 1. If K is less than 1, then you'll lose criticality. You won't sustain criticality. If K is greater than 1, then the reactor is supercritical and the reaction diverges. That's what happens in a bomb, and that's what happens often, or could happen, in a reactor accident. That's what happened at Chernobyl. It's not what happened at Fukushima or 3 Mile Island. Now, the formula is this so-called 4-factor formula. These 4 factors, I'm going to describe what these are, and I'm going to explain how this works, and I'm going to set you a homework assignment. So the homework assignment is that this equation appears on a blackboard in the background in Big Bang Theory. So you have to go home and watch all the episodes of Big Bang Theory until you find the one with this one in the background. And whoever drew it up wasn't a physicist, because their infinity sign is written up as like this. It's like Q instead of K infinity. But it's there in the background in Big Bang Theory. All right, so this is a picture that describes how the neutron cycle works, and it explains what these factors are in the neutron multiplication factor. Now, K infinity, the sub-infinity, means that we're imagining we've effectively got an infinite reactor core. So we're pretending we don't have any leakage or losses of neutrons out of the reactor. So here we start the process with 1,000 thermal neutrons. The equivalent energy of a thermal neutron. This corresponds to a temperature of about 25 degrees C, 0.025 electron volts. We get thermal fission. This is the first factor in the four-factor formula, eta, Greek letter eta. So for natural uranium, this is 1.3, so 1,000 neutrons becomes 1,330 neutrons. These are fast neutrons. They have energies of the order of 1 or 2 MeV. Those neutrons can induce some fissions, mainly on the uranium-238, not because it has a particularly bigger cross-section, but just that there's more of it in the fuel. Remember that a typical power reactor will have a fuel enrichment of 3 to 5%. So 95 to 97% of the fuel, the uranium in there, is 235, and you get a few extra neutrons produced from fast fission. So this epsilon factor is typically just a little over 1. Now we can have some losses, some leakage. Let's go past those and we come to this moderation process. I'm going to talk about moderation in more detail in a couple of minutes. This is the process of slowing down the neutrons from 2 MeV to 0.025 electron volts. Now this process I'll talk about, you can have losses. You can have losses due to resonance capture, which I'll explain. It's this quantity P, which is called the resonance escape probability. It takes out some neutrons. You can have some thermal losses and leakage. Then you have the thermal capture on the fuel. And at the end, you're left with 1,000 neutrons to continue the cycle. So this is a picture of a reactor in equilibrium. Now, to talk a little bit more physics, I need to talk about cross-sections. Who's heard of cross-sections? Who's heard of physicists talk about cross-sections? A few people have. For the benefit of those of you who haven't, let me spend a minute or two explaining what a cross-section is. So let's pretend that we've got a beam of neutrons hitting some target material, and in that target material we've got some target atoms that I've made in the darker colour here. We've got a thickness delta X. This is the side view. We look at it from the front. We see that the target contains these target nuclei that have an effective cross-sectional area. So it represents the effective area to the incident neutrons. So if we work out the probability of fission now, let's say we're talking about the so-called fission cross-section, the probability of fission is the blocked area of this beam spot, this yellow spot, compared with the total beam area. We assign an effective area to each nucleus, and that's the cross-section. So that's what the idea is. It's the effective area encountered by a beam. Now, in reactor physics, we usually talk about neutrons, neutron densities, and you can work out the rate of fissions per second per unit volume. And what you find is that the fission rate depends, of course, on the number density of the uranium-235. It's going to go up as the uranium-235 density goes up. It's going to go up with the cross-section, and it's going to go up with another quantity that we call the neutron flux, which is essentially the number of neutrons times their velocity. So we need this idea and this concept. Cross-sections in nuclear physics are usually in the units of barns. One barn is 10 to the minus 24 square centimetres. And yes, the name does come from sick jokes about couldn't hit the side of a barn. Now, you can work out the cross-sectional area of a nucleus if you know its radius. It turns out that at fast neutron energies, the cross-sections for fission on both uranium-235 and 238 are around about the geometrical cross-section. A real cross-section is going to be bigger or perhaps smaller than the geometrical cross-section. Why is that? Why would that be? Why would its effective cross-section be bigger or smaller? Anybody willing to have a go? Absolutely right, forces. So you might have a repulsive force, which reduces the probability of an event happening, or you might have a favourable force that makes it more likely. Okay, so our chain reaction, we have a fission rate which depends on the neutron flux, but the neutron flux depends on the fission rate. And somehow or other we have to balance these things. Now in a thermal reactor we have a couple of knobs, so to speak, that we can play with. We can change the uranium enrichment, which will change the number density of the uranium-235 in the fuel, or we can affect the cross-section by looking at how it changes with energy. So here's the fission cross-section in barns as a function of neutron energy. Notice the log scale. This diagram up here shows the distribution of neutrons. Now this looks different than the one I showed before because I've now put it onto a log plot, but it is actually exactly the same distribution. This is the fast neutrons. This is the thermal energy regime. There's no thermal, I probably should have put the arrow over here than there, but your cross-section for uranium-238 dies here. So there's no thermal fission on uranium-238, but on uranium-235, the cross-section for fission goes up by about a factor of 600. So if you can slow down these neutrons, you can increase their probability of inducing fission by a factor of 600. This is why the early reactors were thermal reactors, and the early reactors had to work with natural uranium, which is only 0.7% uranium-235. Now, observe, in slowing down, the neutrons have to go through this resonance region, so-called resonance region. There's a high probability that they'll be absorbed here, which is okay if you're looking at uranium-235, but it's not so good if it's 238, and I'll come back to that in a moment. Let me first of all point out this feature here, that at low energies, this cross-section is a straight line on a log-log plot, and that comes about because the cross-section is effectively proportional to 1 on the neutron velocity. So it becomes a straight line on a log-log plot. And that turns out to be useful, and I'll mention that again in a moment. Okay. This is thermal, well, it's not thermal, it's neutron capture in the resonance region of uranium-238. Notice that this goes up to nearly 10,000 barns cross-section. So in the moderation process, the neutrons, in effect, have to run the gauntlet through this resonance region to become thermalized without getting captured. So here's a cartoon. Here's our fast neutron. It's got to run through here, get thermalized, run the gauntlet, try to get through here without getting absorbed. Now, you look at this cartoon and you say, well, why does he bother to go through there? Why doesn't he run around the outside? And that's exactly the way thermal reactors are designed. So remember we looked at this picture of a fuel assembly for a pressurized water reactor. We saw that the pellets are about the size of the tip of your finger, and they're in fuel rods that are about 1 centimetre diameter. This geometry is designed with the idea that when you have a fission in the fuel rod, the neutron can get out of the rod quickly before it has a chance to be captured in this resonance region, so it wants to get out at high energy and then get slowed down in the moderator and then eventually drift back at thermal energies to induce another fission. What makes a good moderator? Well, we've got to slow the neutrons down, so we have three things we want to do. Neutrons don't have a charge, so you can't slow them with electromagnetic forces. All you can do is use, well, I was going to say billiard ball collisions, but it is like elastic collisions. The best ones are collisions between a neutron and a proton. A head-on collision between a neutron and a proton will stop the neutron and give the energy to the proton. So in that sense, hydrogen would be the best moderator from the point of view of losing energy. The figure of merit, or the quantity that describes this loss of energy per collision, uses the Greek letter xi. It's called the logarithmic energy decrement. It's best for water because it's got hydrogen in it, and it gets worse and worse and worse as you climb up the periodic table. You want elastic scattering. You want the neutrons not to get absorbed, but just to get scattered. So you want a good, high elastic scattering cross-section, and you want minimal capture. So when you work this moderating ratio out, turns out that ordinary water is okay, but not great. D2O is absolutely fantastic, and carbon is also a factor of 3 better than H2O. So this is part of the reason, or in fact the main reason, why a light water reactor has to have enriched uranium. It's because this moderator captures neutrons. D2O, small capture cross-section. Carbon, also a small capture cross-section. All right, so we know how to moderate now. Let's look at the effect of enrichment on this quantity eta. Eta is the number of neutrons emitted per absorption on the fuel. So that means both the uranium-235 and the 238. Yesterday, or even in the slide this morning, I reminded you that you get 2 or 3 neutrons per absorption on uranium-235. That's this quantity nu. We then look at how many we're going to get on the fuel. So we have to multiply this quantity by the fission cross-section and divide it by the sum of the fission and the capture cross-sections. So at thermal energy, fission only comes from the uranium-235, but the capture has to include the capture on uranium-238. And if you evaluate this and work out eta as a function of the enrichment, you see that the function looks like this. You can see that if you have 5% enrichment, you've already got a big fraction of what's achievable. Now at 20% we have of what's called the threshold between low enrichment uranium and high enrichment uranium. You don't, you know, it's a proliferation issue if people have highly enriched uranium. So the highly enriched uranium is never used in power reactors. And it's increasingly being replaced in research reactors. But 5% for a power reactor is pretty good, and it doesn't really pay you to go much above 5% enrichment. How do you enrich? Well, once upon a time it was done by gaseous diffusion, but now it's nearly all done by centrifuge cascades. The difference in the mass between uranium-235 and 238 is 3 mass units out of 230 odd. It's not very much. And what's used is this centrifuge technology. So you spin the gas in the centrifuge, and the lighter isotope tends to go to the outside, and so you have a cascade of these centrifuges to enrich. Oop, what happened? That's not meant to be there. It might be a mistake later on. So this is what Urenco centrifuges look like. The Urenco company is probably one of the bigger players in uranium enrichment at the moment. Australia actually was, in the early days, involved in developing centrifuge technology here in Sydney, in fact, at Lucas Heights. But there was a change in government and a decision was made that we wouldn't go that direction, so this technology was scrapped. All right, thermal utilisation factor. Let me just point this one out. This is just the neutron absorption in the fuel compared with the total absorption in the core. So for a thermal reactor, that's essentially the absorption in the fuel, the uranium, compared with the absorption in the moderator. This quantity is less than 1. Now, one of the tasks I get my students to do is to evaluate these things and make a plot like this. So we've got here, what we're doing is we're looking at the ratio of the moderator to the fuel in terms of number density in the atoms. And we're plotting the resonance escape probability and the thermal utilisation factor. Eta is a constant. We're ignoring the epsilon, which is also more or less a constant and near unity. And you see the trade-off between these two things gives you a K value that comes up to a peak and then goes down. Now, when you design a reactor, you want to operate it over on this side of the curve because when the temperature goes up, that has the effect of making this moderator to fuel ratio go in this direction. So what you want to happen is when the temperature goes up, you want the reactivity to go down. So a good reactor will have this kind of a design. The Chernobyl reactor did not. It's hard to find detailed numbers for pressurized water reactors around, but here's detailed numbers in the neutron cycle for a CANDU 6 reactor in equilibrium. You may not be able to read it there, but this reactor is running on natural uranium, and about half of the power, half of the neutron production is in fact coming from plutonium-239, which has been made in the reactor core through neutron captures. Here's our diagram that I started with 1,000 there. This has the 1,000 at a different point. It has it for the fast neutrons here. But you can see the numbers around the curve, and they're somewhat similar to what I showed you earlier on. All right, now, we want to control the reactor. We want to maintain K near 1. And nature has been very kind to us in a number of ways, and I'm just going to list 3 ways here where nature has made it easier for us to maintain criticality, stable criticality in a thermal reactor. The first one is delayed neutrons. The second one is these 1 on V cross-sections at thermal energies that I pointed out. And the third one is Doppler broadening. So we can define a time constant for this reactor period, the time for going around that circle from one generation to the next. The moderation process takes about a microsecond. So in a light water reactor, it was on a slide, I didn't highlight it, but it takes about 20 collisions of the neutron in about a microsecond to slow that neutron down. Then it wanders around in the core for about 1,000 times that time for about a microsecond. Then, on average, it'll be either absorbed or initiate another fission. Now, remember that there's about 0.65% of the neutrons from fission are delayed. They come after a beta decay, and the average delay time is about 12 seconds. This makes a huge difference to what we call the reactor period, the time constant. So you have effectively an exponential growth if k departs a little bit from 1. So here I've got the logarithm, and the time in seconds assuming no delayed neutrons, and a K value that's 1 part in 10 to the 5, different from 1. And this thing diverges very quickly. You put these delayed neutrons in, I've now made K only 1 part in 1,000 with the delayed neutrons, and it diverges much more slowly. So this tiny fraction of delayed neutrons has a huge impact on the reactor period and the ability to control it. 1(V) cross-sections also help us. Remember I pointed out that this product of the neutron flux and the cross-section, if we go backwards into the formula, we've got the number of neutrons times their velocity times the cross-section. So if the cross-section is proportional to 1(V), that factor cancels out, and you end up that the fission rate is independent of the neutron energy. So you can have slight temperature variations that will change around the neutron energy, and the reaction rate will remain insensitive to the core temperature. So that's good. The other thing that helps us is Doppler broadening. Has anybody heard of Doppler broadening? People know about Doppler broadening? Do you know what the Doppler effect is? Yeah. So in spectroscopy, if you have thermal motion, for example, in your source, then the spectroscopy lines, the lines will get broadened. Their frequency will get spread out. The same thing can happen here with these resonances. So the fuel gets hot, the atoms jiggle around more, and the effect is that these resonances get broadened, and it increases the likelihood of the neutrons getting captured. So as the temperature goes up, the Doppler broadening eats more neutrons, which slows down the reaction rate, which helps keep and restore equilibrium. So there are three things that help control the reactor. We won't say a lot about control rods. These are neutron absorbers that are deliberately inserted into the reactor to control it and to balance the neutron flux. So these are chosen from materials that absorb neutrons. They can be chosen to absorb primarily at thermal energies or at what are called epithermal energies, between fast and thermal. And sometimes they can be an alloy. Here's an example. Silver, indium, cadmium. So this is a good material to operate in the reactor, and it absorbs neutrons in an appropriate way to control the chain reaction. Now, I want to talk about actinide production. We've now got our reactor running. It has fuel in it. I think I mentioned in the question time yesterday that the average time that a fuel assembly spends in a power reactor is the order of 3 to 5 years. So it'll go in fresh, it'll be shuffled, and then it'll come out. So it's perhaps intuitively obvious. After you've worked in quantum mechanics, nothing's ever obvious again, I think. But I think it's reasonable intuitively that the neutron flux is higher in the centre of the reactor core, so you'll tend to get the fuel used up faster in the centre. So typically there'll be some shuffling of fuel assemblies on a refueling when new fuel is put in. Now, in the time that our reactor fuel is in there, remember that it's mostly uranium-238, not fuel, but most of the, well, it is fuel, but it's in the fuel. The uranium-238 captures neutrons, 2 beta decays, becomes plutonium-239, half-life of 20,000 years or more. It, in turn, captures neutrons. So it can capture a neutron, become plutonium-240, capture a neutron, become plutonium-241, 14-year half-life. This stuff decays to americium. Capture neutron, capture neutron, capture neutron, decay to curium. So what's happening here is that we're climbing up the periodic table. So this process was used in the early days to discover new elements. Some of these materials are useful. Americium-241 is widely used in smoke detectors. But when it comes to nuclear waste, it's these guys that are the long-lived activities that are a pain. All right, let me say a little bit about alternative reactor technologies. We've talked a lot about thermal reactors. I won't say a lot more about thermal reactors. I'd like to say a little bit about fast reactors. I'll say a little bit about thorium, and I'll go fairly quickly with a show and tell through the Generation 4 reactor designs. So we saw that the cross-sections, you can get fission on both uranium-238 and 235 at fast neutron energies. But the cross-sections are small. So how do we overcome that? Plutonium-239, similar cross-section to uranium-235. Plutonium-239, from the point of view of its cross-section, is not going to be a lot better than uranium-235. But what is better is the number of neutrons per fission. So you see two things happening here. One is, in this column, we've got uranium-238. The number of neutrons per fission goes up a little bit when you go to fast neutron-induced fission. Same thing with plutonium, goes up a little bit. But plutonium has significantly more neutrons per fission than uranium-235. So your plutonium-239 is often talked about in fast reactor cycles because it's got this improved neutron emission. It's in fact no good at thermal energies because the plutonium captures neutrons without fissioning at thermal energies. So you can never talk about breeding with plutonium at thermal energies. So we're talking now about fast reactions. So if we take eta minus 1, this is the number of neutrons that's available for losses. It helps us run a fast reactor. And if we have extra neutrons available, then in principle we can use that extra neutron to make more fuel. So our fast reactors have no moderator. That means you have to have a high atomic number coolant. You want something that the neutrons are not going to lose energy when they interact with it. We'll take out our fast fission factor. Our thermal absorption, well, it's no longer thermal absorption, but our absorption on the fuel is going to be reduced because of the cross-section. Our resonance escape probability is going to be better because we're not slowing the neutrons down, so this P will be better. What we can do about the eta is increase the neutrons per fission, so that helps a little bit by going to plutonium or to higher energies. And the other thing that we have to do is increase the uranium-235 enrichment. So these extra neutrons in the plutonium allow for what's called breeding. So this is making new fuel out of fertile material, fissile out of fertile. And it was the original motivation for fast reactors. Now that was back in the 1950s when it was thought that uranium reserves worldwide were quite small. Turns out that uranium is more prevalent than we thought. So this motivation for fast reactors has gone away. There's a few fast reactors on the grid. Here's an example of one news item, one operating in Russia. It's a sodium-cooled fast reactor. It's been operating for more than 30 years and it works fine. The Russians have put online a new BN-800. It's a slightly higher power sodium cooled fast reactor. This is a pool type reactor. You have a pool of sodium, and in principle it can breed some fuel. The motivation for breeding has waned, but people now see these reactors as plutonium burners. So the idea here is actually a good one. The idea is to get rid of plutonium from weapons and use it to make energy. They're also seen as actinide burners. So these are these heavier elements that we've created in our thermal reactor waste. A lot of those actinides can be burnt to get energy, and that would then make our nuclear waste more manageable. They're probably not going to be a big player in energy production in the near future, I think. Thorium reactors. Regularly hit the news as the solution to our nuclear problems, and one should view those news items with a good degree of scepticism. I've pointed out last time that thorium's not fissile. You'd have to start with uranium-235 anyway. Neutron capture to thorium, 2 beta decays and make uranium-233. In principle, can be done. The alternative is this uranium to plutonium that we've been talking about. Now, without going into details of the materials and all the other problems associated with making thorium reactors commercially viable, I'll just point out one thing. They're potentially a long-term prospect. There's been research into thorium reactors since the 1950s, but there's still a lot of technical impediments that either make the thorium reactors impractical or, if not impractical from a purely engineering point of view, impractical from an economic point of view. And one example is here. You see the decay processes, both cases involve a neutron capture and 2 beta decays. Neutron capture, 2 beta decays. The first beta decay, 22 minutes, is much the same in both cases. Now, this graph here shows how you produce an isotope you want as a function of time, where the mean life here is 10 units. So you can see that up to about 1 mean life, you get more or less linear production. And after that, you're not winning so fast. So the idea, if you're breeding material, would be to just leave it in the reactor for the order of a couple of half-lives. No more, it's a waste of time. That's all right. That's the same for the uranium and the thorium cycles. The big difference is then when you get to the next decay. In the uranium case, it's 2.5 days, but in the thorium case, it's 27 days. Now, if you want to wait, say, 10 half-lives to get all the neptunium converted to plutonium, you only need to wait a month. But in the case of the thorium, you have to wait closer to a year, and that then becomes a nuisance and makes it just less favourable. And there's a number of other aspects that make the thorium cycle uneconomic at the moment. A lot of the advantages that people talk about for the thorium cycle involve particular reactor designs, but those reactor designs are not unique to thorium. All right, let me say a little bit about Generation 4. Generation 4 reactors, these are the revolutionary reactor designs. This is a worldwide initiative with many countries involved. And the goals are sustainability, so up to 300 times more energy from the nuclear fuel, shorter-lived radioactive waste, actinide burn-up. So this is together with consuming existing waste as well, to use existing waste as a fuel. Competitive nuclear energy, so looking for design simplification, modularity, cheaper power, to try to get over this obstacle at the moment where a nuclear power plant has a huge upfront investment cost. Synergies for process heat, hydrogen production. We start to run out of petrol, what are we going to run our cars on? Maybe electricity, maybe we'll need hydrogen. Probably I'm not keen on a hydrogen car, but anyway, we'll see. Improved operational safety and, importantly, proliferation resistance and physical protection. So these are very good aims. So the 6 chosen designs, 3 of the 6 are fast reactors, and some of the others can be either fast or thermal reactors. And I'm just going to step through these and show you, to give you a little bit of a flavour of the different kind of reactor types. You can find a lot of information about Generation 4 reactors online easily, so I'm not going to attempt to explain any of these in great detail. So the first one here is a very high temperature reactor, gas-cooled reactor. The idea of this one is that you would get very high temperatures that could be used for hydrogen production or process heat. It uses these pebble fuels where you have your uranium surrounded by carbon in a kind of like a ball. There's been a lot of research into this kind of fuel in a number of places. Now, this is where that slide that got out of place was supposed to come. Maybe I should just skip it. This one. Yeah, high temperature gas reactor experience. So there's been a huge number of experimental reactors around this kind of design, and to get me back where I was, I hate doing this stuff, try to avoid it. The Chinese have just recently, fairly recently commenced construction on a high temperature gas reactor. So that's one type. Gas-cooled fast reactor. This is using gas cooling. There's no precedent for this kind of reactor. It's a fairly radical, revolutionary design, and it'll be some time before there's even an experimental version. Sodium-cooled fast reactor, well, we already have these, and I just talked about them a minute ago. So this is an extension of that concept, and basically it works now. So again, there's activity in China exploring this sodium fast reactor technology. Lead-cooled fast reactors. The Russians for a long time have used lead-cooled reactors, so they have lead as the coolant. It's a fast reactor. Perhaps the disadvantage of these is, of course, lead is dense, so they're very heavy reactors, and you've got to worry about the consequences of that weight in seismic activity. But the Russians have developed this technology quite well, and it promises some advantages with further development in the future. Molten salt reactor. This is an interesting one. This is the one that's often talked about in terms of thorium reactors. In this case, the fuel is a salt, often proposed liquid fluorides of uranium and plutonium. And I think perhaps the interesting thing about this reactor design was where it started out. And you almost think this can't be real, but it was. This reactor design was considered for aircraft nuclear propulsion in the 60s. What could possibly go wrong? Completely crazy idea. So this is not Weinberg, the theoretical physicist. This is Weinberg, who was the director of Oak Ridge National Lab at the time. And he was a bit frank, you know. We didn't think it would work, but we didn't turn down the funding. So at least it's a precedent for a Generation 4 reactor, and it may have some good things come out of it. It was interesting, I did get to see some of the hot cells and regions where they now use these actinides for targets for making new elements at Oak Ridge. And they had this beautiful building full of hot cells built for this program, and a number of them had never been used. But they're still there, and they're still put to use when useful, when needed. Supercritical water-cooled reactor. You can have supercritical steam generation with conventional power plants. The idea is to try to use that technology with nuclear plants. Somebody asked me at dinner last night, why do we settle for 33% efficiency, thermal efficiency with nuclear power? Well, that's what thermodynamics gives to us. The temperature that you present the steam to the turbine determines the thermal efficiency. If you can get the temperature up, you improve the thermal efficiency. And so the idea is to use this supercritical water, supercritical steam technology in the nuclear context. This is a big challenge because when you have this supercritical heated water coupled with a radiation environment, you've got a lot of materials and technical challenges. All right, so that was a quick look through Generation 4 reactors. So there's still a lot of ideas out there. A lot of the old ideas come back and are being reconsidered as materials developments progress. Let me say a little bit about accidents and safety strategies. There's 3 accidents that I want to mention. 3 Mile Island, United States, 1979. Chernobyl, Ukraine, 1986, and Fukushima, 2011. Now, can I have a show of hands? Who's heard about Texas City 2005? Anybody know about this accident? Before my lecture, so did you heard of any of these? Yeah. You know what this was? This was an oil refinery. It killed 15 people. It hits the news and then it disappears. Anyway, back to nuclear. So what happened? 3 Mile Island was a pressurised water reactor. It was a loss of coolant accident. There was no breach of containment. There were some fission fragments released, some radioactivity released, but it was a tiny amount, and you can honestly say the health consequences are negligible. Contrast Chernobyl in Ukraine. This is a Russian reactor, RBMK, terrible reactor design, originally designed as a plutonium production machine, not a submarine engine. No containment, blew away the core, killed people, significant health consequences. Fukushima in Japan, tsunami, boiling water reactor, loss of coolant accident similar to 3 Mile Island, damage to containment. There has been radioactive waste release. It's very small compared with Chernobyl, but it's a huge mess to clean up. Some on-site plant workers got their lifetime dose in managing this accident. So why do accidents happen? Well, 3 main things: plant failures, human failures, and external events, and sometimes a combination of all 3. What can we do about it? Well, the International Atomic Energy Agency has guidelines which are kind of outlined in this diagram here. At the centre of it is this idea from military what's the word? Technology, strategy of defence in depth. But with reactors, you need to start with appropriately siting the reactor. You want high quality in the construction and design. You want a robust and proven design. And then you want these levels of defence. You want, as first level, prevent failures from happening in the first place. Second level, when you do have a failure, detect it and control it. You then need to control cases where you have accidents. They talk about design basis as opposed to severe accidents. Several levels. Eventually, at the fifth level, you need good emergency plans. And around these particular strategies, you need comprehensive testing, sound operational practices, safety assessments, oversight and regulation. It's very important that the operator is overseen and regulated by a body that's not too cosy with the operator. And then around the whole thing, you need a safety culture where anybody in the plant has the right to say, no, stop, wait. We need to think about this before we take this action. So here's one of the ideas of defence in depth applied to physical barriers in a pressurised water reactor. And the idea is that if you have some problem with your fuel, then the first line of defence is the fuel cladding, and hopefully that can contain the radioactivity or the problem. If that fails, the next level is the pressure vessel. If that fails, you have a steel liner inside the containment building, and then you have the shield building. Now, at least in 3 Mile Island, this containment basically worked. So the reactor was broken, but it stayed inside the reactor vessel. 3 Mile Island. This is the control panel, very 1970s. What happened with this reactor was that there was a fault. It's in fact a known fault or a common fault in the secondary cooling circuit, which caused a reactor trip. So the reactor scrammed, it tripped, turned itself off, but you still have decay heat. So you need to keep the core cool. So the secondary system cut in, but there'd been maintenance done and they hadn't opened the valves on the secondary cooling circuits. That was one problem. The other problem was this PORV, pilot operated relief valve. It got stuck open, but the indicator on the control panel said it was closed. So this led to the operators doing the wrong things. They weren't very well trained anyway to deal with emergency situations, but they were fed false information. So this led to uncovered fuel, which led to severe core damage. When the fuel rods get hot, they have zirconium in them, which reacts with water and releases hydrogen, which caused a small explosion. The reactor was destroyed, but fortunately there was a small radioactive release. In terms of the consequences, this had a huge impact on the perceptions of nuclear power. I'd say this was probably the point where a lot of people went from being pro-nuclear to anti-nuclear. There was public panic and unclear information from authorities. So this had a huge impact. This was just to point out that the decay of these fission fragments, there's still a lot of heat can come out of the fission fragments once you turn off the reaction. A lot of lessons learnt. There was faulty equipment, there was poor design. I mean, some of the problems in the control panel, the metering was okay for normal conditions, but in fault conditions, meters were off scale, so people had no idea what the real number was. Human error. Chernobyl. How am I doing for time, Chris?
We've got about 5 minutes up until the hour, but we actually started early, so we've got plenty of time.
Okay.
So if you maybe another 10 minutes.
Yeah. That'll be good. So Chernobyl is the one that's the real killer. So this is this Russian-designed graphite-moderated light water reactor. Had a positive void coefficient. This accident was really entirely human initiated. So I think the plant had been up for about 2 years, and some of the safety tests that were required hadn't been done. And so this accident actually started out to do a safety test. So the idea was to turn the reactor off and see if you lost off-site power as the turbine spun down, would there still be enough energy to provide cooling power and operate systems until the emergency systems clicked in. Well, what happened was that the power was dropped in preparation for this test. That's okay, but they also disabled safety systems. They overshot the power reduction, which leads to this xenon fission fragment poison buildup. Then there was a request from the grid to maintain power, so they tried to raise the reactor power again, pulled out control rods. Everything was... Somebody had said at this point, hey, wait a minute, we've lost control of this thing. We just need to shut down, go away. Would have been fine. But they decided to go ahead with the test. Somebody flipped the switch to turn off the load to the steam turbine. That set the temperature in the reactor up. It's too late. Within 4 seconds, the reactor power went up by a factor of 100. There were steam explosions in 5. It wasn't a nuclear explosion, it was just the heat went up which generated steam which caused an explosion. But then, sorry, I want to go back. But then there was fire and dispersal of the fuel in the moderator. Overall, it's estimated that about 5% of the core was dispersed. So this one, human error, terrible safety culture, and a rotten, really rotten reactor design. No containment. No reactor like that would ever have got licensed in the West. A lot of consequences. People died. Estimates of the cancer deaths depend on who writes the report, but of the order of 50 people were killed as a direct consequence of this accident. These RBMK reactors have continued to run post-Chernobyl. One of the things that was done was to increase the fuel enrichment. And when I first read that, I thought, that sounds crazy. You're making it safer by putting more fissile material into the core. But the reason it works is because of this graph I showed you here. Increasing the fuel enrichment from 1.8% to 2.4% is enough to move you from this operating point over to here on the curve and make the reactor safer. The Soviet Union has opened up a lot more, and there's huge changes in safety culture. This is the Chernobyl site now. They're just finishing putting this structure over the site. I guess this will stay there for hundreds of years. Fukushima. This accident was instigated by a tsunami which came over the barrier. And you can see, even on the plant, there's a couple of metres of water along the side of the reactor building. The tsunami had tripped the reactor, but again, this is bad design. This was, I think people are being prosecuted for, not taking advice on some of the safety strategies. The diesel generators for the backup power are effectively in the basement, and when the tsunami came in, it flooded the diesel generators, which meant that although the reactor was turned off, there was no way to cool the core. And this decay heat, again, overheated the core. It led to this oxidation of the zirconium fuel cladding, which creates the hydrogen gas, And it was the explosion of this hydrogen gas that made these spectacular booms, bangs, explosions that hit the media. A lot of trouble, huge mess to clean up. Yeah, a lot of things went wrong. So a lot of lessons have learned here. There's still a huge clean-up activity. One of the questions that came up here that I think is unique, or well, is fresh. When you have accident management, who takes the decisions? And this was a factor because people on site weren't able to make decisions. They had to go up the tree to get authority to take action. And perhaps the accident wouldn't have been as bad if somebody local had the authority to make the decision. And I think the clear message here for me too is that the relationship between the operator and the regulator shouldn't be too cosy. Now, Fukushima nuclear accident was bad. I don't want to trivialise it. But this is the kind of thing that hit the news lines. Breaking news, over 25,000 dead in nuclear disaster. Japan battles nuclear emergency, 10,000 feared dead. Japan radiation levels 10,000 times above normal. Well, this is just sheer lies, right? No one died as a result of the radiation release. I believe there might have been some industrial accidents that killed a couple of workers. Certainly, when there is a disaster like this, if you make a decision to evacuate, some people will die. It's inevitable that some frail old people, the process of moving them and evacuating them in a large enough population, some people will die. And it's a hard decision, I think, for authorities sometimes to make. Should we evacuate or should we not? Certainly, the deaths associated with Fukushima, even factoring in long-term radiation effects, not a big player compared with the deaths from the tsunami. Now, yesterday I put up a statement that nuclear power is safe. I'm not going to try to convince you one way or the other, but I want to show you this table, which comes from a review that the Australian government commissioned about 10 years ago, uranium mining, processing nuclear energy review. And they've listed in this table severe accidents. We can ask what's the definition of severe. This is prior to Fukushima, although adding Fukushima into these statistics doesn't make any significant difference. But if you look at the direct fatalities per gigawatt electrical per year, nuclear does well compared with the other baseload power technologies, whichever way you take the numbers. So it's this kind of table and data that leads people to say that nuclear is safe. What I suggest that you do is that you look into it yourself and make up your own mind on these things, but don't necessarily believe everything that people say. Very rightly, post-Fukushima, the world stopped constructing nuclear reactors, paused, looked at their safety cases and strategies, looked at their regulation and legal frameworks, and now construction has started again after people have done those reviews. Okay, I should finish. Yeah, let me just say a little bit about waste management. This is the whole nuclear fuel cycle. I've said absolutely nothing about the front end of the fuel cycle, which makes nuclear fuel. I've talked about the reactor. After the fuel has been in the reactor, it will be stored for a period, usually on site at the reactor, and then there's two paths it can go. It can go through for reprocessing, which could make plutonium that could go back in and become fuel again. The leftover stuff from the reprocessing can be made into a glass-like substance and then disposed, or you could go for direct disposal. I'm going to say just a little bit about this now. So most fuel is currently still sitting on reactor sites because, well, it depends which country you're in. Initially, it's stored on site in a spent fuel pool while it cools down, while the fission fragments decay and the radioactivity drops. But in the spent fuel, there's fission products. There's uranium-235, which actually, after irradiation, still has a higher enrichment than is in natural uranium. And then there's a certain amount of plutonium isotopes. So you can view this plutonium as waste or as a resource. You can say, should I just reprocess it or store it, or should I just dump it? And the decision there is usually made on other grounds than economics. Other grounds than economics. The economics are not clear, and the process of reprocessing is often linked with making weapons. So it's one reason that the United States made the decision in the Jimmy Carter regime that they would no longer reprocess for civilian purposes. In France, they do reprocess. There's a whole lot of numbers here. I'll just point out that the high-level waste in the end, which has 96 to 98% of the radioactivity, ends up being 0.2% of the volume. So your very high-level radioactive waste with the reprocessing can be reduced to a small volume. Typically, it's made into a glass, it's vitrified, which is put in a container that looks like this. So this is about 45 centimetres across and a metre and a bit high. There's also an Australian invention, Synrock, which is an alternative to this vitrification process. Probably the most advanced case for an underground repository is the Swedish plan. They are going for direct disposal. Essentially, they just take their cladding tube and fuel pellet, put it inside a canister, and then bury that deep underground, surrounded by clay in bedrock that's nearly 2 billion years old. And in the first lecture, I talked about these Oklo natural reactors, which operated on the Earth 2 billion years ago. We can look at where the radioactivity has gone in these deposits, and it turns out that it didn't go very far at all. So to some degree, these things have been an experiment for us and a prototype for this deep underground repository. Okay, I think I might skip that. Waste management has a checkered history. This is a table from a review that's 15 years old now. And if you read the detail, there's lots of plans and lots of talks and lots of postponing. And unfortunately, that's the way it's continued. My view is that there are good technical solutions. The obstacle is social license and political will. Ultimately, action is going to have to be taken, but we can get away with procrastinating to some degree because really the volume of this material has not got out of hand yet, and maybe that's why governments are able to get away with not making decisions. Well, I can come back to the pros and cons. I think given that I've used up my time, I probably should just finish. Thank you.